So we just listened to some discussion of a statistical study on number of hours of sleep people get and its association with increased cause of mortality from for those people associated with metabolic syndrome. Now, they mentioned in the study that the proportion of Americans with metabolic syndromes is somewhere between 30 and 40%. Now, when you take a sample and you calculate the proportion, you get something which is called a point estimate. It's just one number. That's your point estimate. And our notation for a population proportion is p hat. Now, we're hoping that that's a good estimate of the population parameter, which is p. And that's what we hope when we sample anywhere, anytime, is that our sample gives us a good estimate of the population parameter. That's why we're sampling. It's often impossible to actually get the population parameter, because to get the population parameter, you'd have to have data from everything in your population. So that's usually difficult, if not impossible. Let's do a couple more here just to refresh our memories a little bit. What's the notation for the sample mean? X bar. And the population parameter that it estimates is mu. How about for the standard deviation? What do we use for the standard deviation? S. And the corresponding Greek letter, the parameter, sigma. Thank you. So what we're hoping when we calculate when we take our samples is that this is giving us some good information about the population parameter. Unfortunately, if you take a different sample, you're probably going to get a different estimate of that population parameter. So what do? What's the correct value? Well, we don't often know. So what we'll do is we'll give ourselves a little range. We'll say, okay, it's somewhere between these numbers. And so that's what we're going to do, is we're going to work on giving ourselves a confidence interval. So if I wanted a confidence interval for something like this, our parameter p, the population proportion, what I could do is start out with my point estimate. So this is our point estimate, and surround it by a little wiggle room. What do I mean by that? Well, I'm going to say p hat minus a little bit to p hat plus a little bit. And that little bit is denoted with an E, represents our error. And I can give you the formula for that in a little bit. Let me give you the formula right now. E is going to be z sub alpha over 2 times the square root of p hat times q hat divided by n. So that's our error formula. So one of the things we're going to need here is a little bit of understanding of z sub alpha over 2, what's alpha, etc. So let me talk a little bit about that. P hat is our point estimate. That's what we guess the population proportion is. Anyone want to venture a guess as to what Q hat is? We know what P hat is. Our number of successes divided by the total number in our sample size. So successes over sample size. Yeah, it's kind of like your failures. The easiest thing to do is say that it's 1 minus p hat. Okay, it's your failures. So you're one or the other, success or fail. Now z sub alpha over 2 is part of the calculation of our error term. Let's keep in mind what z sub alpha is. Z sub alpha is the area in the right tail of a distribution. So z sub alpha over 2 is going to put alpha over 2 of the area, or that little portion here. Let's see, they're using a different color. This one. This area is going to be alpha over 2. So I want to find that point from the z distribution, z sub alpha over 2. Okay, so let's practice that a little bit. By the way, what's alpha in this calculation? Alpha is our level of significance, and it relates to our confidence level. So our confidence level equals 1 minus alpha. Let's do a couple problems and just try and get a little bit familiar with this confidence level and this notation. And we'll talk a little bit more about it. But to start with, let's try problem number 8. We want to find z sub alpha over 2 when alpha is, I'm guessing it's 0.04. Yes, 0.04. Alpha is 0.04. So if I plug that in here, it's z sub 0.04 divided by 2, which is z sub 0.02. There's a couple ways we can get at this one. Z sub 0.02 is the point on the standard normal curve with 2% of the area in the right tail. So that's right here. 2%. 0.02 or 2%. Now, if 2% of the area is in the right tail, how much is in the left tail? 98%. So this is 0.9800 of the area. So, two different ways you can come about that number. One of them is kind of the old school method by looking it up in the z table. So let's just do that just one more time for practice. And then we're going to start using technology pretty much from here on out. So I want the area in the left tail to be 98%. So look in the table, look around until you find something close as possible to 0.9800. 2.05 sounds pretty good. Yeah, 2.05. So 2.05 works. And that's doing it, like I said, with the tables. I think you might find it convenient to also use Google Sheets for something like this. This should work. So I want norm inverse. I need to type in the area that I want in the left tail. So that area is 98%, so 0.98 for a distribution with a mean of 0 and a standard deviation of 1. And we're getting pretty much the same thing, except we're getting a few more digits out of Google Sheets here. So whatever you find convenient in terms of finding these things. Are we okay with that first one? Problem number 8. I want to build on that a little bit for problem number 6. So which way do you like finding your z values? Table or Google Sheets? Table? Tables? Okay. This is just like interesting to me. It was such a big thing for me to give up on the tables and start moving towards technology, but you guys like the tables. That's cool. I have no problem with that. All right, so let's take a look at problem number 6. We want to find the appropriate z value for a 99% level of confidence. And we need to find z sub alpha over 2. So first things first, if we have a 99% confidence level, I'll write that as 0.99. 0.99 equals 1 minus alpha. So what does alpha have to equal? Yeah, you can solve for it. So let's see, what do I do? I can subtract 0.99 from both sides and get 0 equals 0.01 minus alpha, and then add alpha to both sides. Alpha is 0.01. Okay, so that's telling me then that I want z sub 0.01 over 2 or z sub 0.005. Z sub 0.005. Charlotte, what does this mean? Z sub 0.005. I mean, if I was to draw this, what should I draw? Or what should I shade? Yeah, 0.5%, but where? Yeah, so we've got 1/2 of 1% or 0.5% of the area has to be in the right tail. Perfect. So this little bit is 0.005. What's that going to leave for the rest of it? Kylie? Yeah, so 1 minus that is 0.995. So 0.995. All right. So for you table lovers, race me. Find the point on the z-curve that has 99.5% of the area in the left tail. Should be about right. Actually, I'll cheat and just go up here. And let's make that a 0.995. All right. So 2.57, 2.58. I think the tables give you 2.57. 2.575. Okay. Oh, they actually, yeah, they split that one. That one's such an important one that they split that one. Thank you. So back over here, z sub 0.005 equals 2.575. Yeah, on your table, that's a special one. So it's kind of broken off. All right, nice. So a couple little practice problems with this notation. And let's move on to some other stuff. Like in problem number 10, they give us a confidence interval. It says express a confidence interval. Now our confidence interval is 0.165 is less than p is less than 0.186. And they want us to express this in the form of p hat plus or minus e. So, okay, I need to figure out, first of all, what's in the middle, and then, you know, how far either direction I'm going to get these values. So I need to figure out what the middle is. That'll be my p hat. And then I need to figure out the error term. Any suggestions on figuring out the middle term? Averages, right? It's just going to be the midpoint. 0.165 plus 0.186 divided by 2. Thank you. 0.1755. Good. Alicia, how am I going to figure out what E is? How am I going to figure out how far I have to move from here to get to here? That's much more work than we need to do. No, we're not trying to find the z-score. We're just trying to say, because what's going on here is I got my original p hat is what's in between these. It's the middle number. And we calculated that, Add these up, divide by 2, you get 0.1755. The question is, how far do I have to move? What is my error? This is going to be p hat minus e. This is going to be p hat plus e. So how far do I have to move to get to 0.165, or up here to 0.186? What's the error? Anyone? Keegan? Yeah, subtract them. So just take 0.186 minus 0.1755, and we find that that error term is 0.0105. And it's in both directions. So that's how far you move to the right to get to that end, and left to get to this end. So we can rewrite this in the form of p hat, which is 0.1755. That's your point estimate for the population parameter. But you know, if you took a different sample, you'd probably get a different value. So you surround this by a little bit of wiggle room. Say, well, it's likely to be in this interval. That interval is created by taking this plus or minus 0.0105. So that's the form of p hat plus or minus e. Tell you what, let's try one that's kind of similar to this, going the other direction. In problem number 12, we're going to start out with this and then write it like what we got in number 10. So doing the complete opposite. Before I move on to number 12, are we okay with what we did here on problem number 10? Yeah, please. Autumn?
So when do we use the error formula? Do we know?
Oh, we'll get there. We haven't practiced using it yet. It's when we start getting to some problems that ask us to do some calculations. Dominic? I subtracted. You could do it two ways. You could subtract the 0.186 minus 0.1755, or you could subtract 0.1755 minus 0.165. It's just the distance between these two. So it's just a subtraction problem. Oh, we found what's in the middle, and what's in the middle is the average of those two. So you add these two up and divide by 2. Okay. Thanks for the questions. Anything else? All right, let's look at problem number 12. This time they're going to give you something with a form p hat plus or minus e. And it's 0.270 plus or minus 0.087. Oops, there you go. 0.270 plus or minus 0.087. And what they want you to do is they want you to rewrite it as p hat minus e to p hat plus e. Just write it as an interval as opposed to your point estimate plus or minus the error term. They just kind of want it, all right, from what to what? Okay, let's see. Sabrina, what'd you get? So, there you go. So you want to take 0.270 plus 0.087 is 0.357. Good. And the other side, 0.183. Okay. Are we all right with those calculations? All right, good. Well, let's try and put a couple things together now and actually find what's called a confidence interval. And that's what this is. P hat is our best guess as to the population proportion, 27%. But we know that if we took a different sample, we're going to get a different sample estimate. So we surround it by this confidence interval. So we can be pretty confident that whatever the true population proportion is between 0.183 and 0.357. Now that to me seems like kind of a large interval. I mean, you're talking about almost 18% to go from top to bottom, but all right, it's our confidence interval. That's where we think the true population parameter is at. But we can't sample everybody, so that's the best we can do. Let's put this to work in terms of problem. We'll do it old school, and then we'll do it on stat disk. So we'll start with problem number 18. It's not letting me zoom in. All right. Gonna have to do it without zooming in. The Genetics and IVF Institute conducted a clinical trial of the Y-sort method designed to increase the probability of conceiving a boy. As of this writing, 291 babies were born to parents using the Y-sort method. That's your N. 239 of them were boys. So, what is the best point estimate of the population proportion of boys born to parents using the Y-sort method? So the best estimate is your P hat. And P hat is simply going to be X over N. So this is your X, that's your N. So 18 P hat equals X over N is 239 divided by 291. So about 0.8213 or 82.13%. So that's part A. That's your best point estimate. But if you repeated this experiment with a different set of parents, different 291 couples, are you going to get the exact same thing? Probably not. Probably going to be a little bit of wiggle room on either side. You should get something close, but what we want to do is we want to surround that by a confidence interval. So in part B, they ask you to construct a 99% confidence interval. Now, if we're constructing a 99% confidence interval, what's that telling you about the significance level alpha? What's alpha going to be? Yeah, 0.01. So 0.99 equals 1 minus alpha, or alpha equals 1 minus 0.99, which is 0.01. Why do we need that? Well, we need that to calculate our error term. E equals z sub alpha over 2 times the square root of p hat q hat over n. I'll be curious to see if you guys like doing this old school or if you want to do this using technology. But we'll find out in just a minute. Do we have to go back and do z sub alpha over 2? I think we got that just a minute ago. It was 2.575. Remember, so z sub 0.01 divided by 2 is z sub 0.005, which is 2.575. What else do I need in order to calculate this? I need p hat, which I've got. p hat, let me write it as a decimal, 0.8213. What's q hat? How do I find q hat? Q hat equals 1 minus p hat. That's going to be 0.1787. N was 291. Okay. Let's put it all together. It's going to be 2.575 times the square root of 0.8213 times 0.1787 divided by 291. I'd suggest you take out your graphing calculators for this one. Although it'd be really impressive if you could do it in your head. 2.575 seconds square root 0.8213 times 0.1787 divided by 291. Now I'm going to do myself a little favor. This is going to be my error term. That's going to be E. And I know I'm going to need to use this number twice. So for my convenience, I'm going to store it. To the left of the number 1 is your store key in X, which is to the left of alpha. Stored in X. You should get about 0.0578. You guys matching that calculation? All right. Now, to construct my confidence interval, let's see. I want p hat plus or minus E. Or better yet, p hat minus E to p hat plus E. That's going to be my confidence interval. Well, I've got E stored here. So let me start with the lower limit, 0.8213 minus that E term, X, 0.7634, call it 7635. On the other side of things, I just want to do the same thing except add, and I get 0.8791. Okay, so somewhere between 76.35% and 87.91% is where we think our population parameter is. We don't know what the true population proportion is, but we think it's somewhere between here. Last question on this one, and then maybe we'll comment on it. Based on the results here, does the Y-sort method appear to be effective? Yes or no? Let's think about this in a different way. If you weren't using some particular method, about how often would you expect a boy? About 50%. Is 50% in this confidence interval? No. In fact, it's well above 50%, isn't it? Not anywhere near 50%. So it does appear that this method is effective. Yeah, absolutely is effective. So yes. Yes. 50% is not in the confidence interval. Now, just because something's in or out of the confidence interval, it might be statistically significant, but it might not be practically significant. I mean, if our confidence interval went from 51% to 53%, are you going to spend thousands of dollars to increase your chances of conceiving a boy 1 or 2%? Probably not. So the difference between practically significant and statistically significant. This would be statistically significant, but not practically significant. This seems to be both. It's not only statistically significant, but it's practically significant. That's a huge increase. There is one more peculiarity about this, and that's how we discuss this. We created this using a 99% level of confidence, an alpha of 0.01. It would be wrong to say that there's a 99% chance that our population parameter is in here. If you insisted on talking about this with probabilities, the correct verbiage would be, say, well, the probability that P is in there is either 1 or 0. We just don't know which one. It's either in there or it's not. There's no real probability associated with it. We just don't happen to know what's in here. What you could say is this procedure, 99% of the time, that procedure will contain the population parameter. We just don't know when it's not going to contain it. If you're reporting this to somebody else, you could say we can be 99% confident that the proportion of boys conceived using the Y-sort method, boys conceived using Y-sort is between, and here we'll list our probabilities, or not the probability, yeah, their proportions, 76.35% and 87.91%. So it's somewhere in there. We don't know where. We're pretty confident that it's going to be in here. How are we looking on this one? Let's take a quick peek at it using StatDisk. So if you happen to have StatDisk on your computer, fire it up. And let's try it using StatDisk. So first click Analysis. And then if you scroll down a little ways, you might see something that looks promising. Confidence intervals. Now there's a lot of confidence intervals there. Which one do you think looks good? Yeah, one sample proportion. So let's go over here. And it asks us for our confidence level. Well, we wanted to be 99% confident. So let's put in a 0.99 there. Our sample size was 291. How many successes did we have in that 291? 239. So you type in all this information and click Evaluate. Wow. So which one do you like better? StatDisk? You sure? I mean, you're welcome to do it old school. Nothing. It's whatever works for you. All right, but yeah, I think using technology is the way to go on this one, for sure. Okay, so let's try some more. And maybe we'll use a little bit of technology to try and get around some of the drudgery work. What I'd like for you to be able to do is understand how to state your conclusion and understand what test to use and when. Sabrina? Okay. I stole that from a previous calculation that we did today. So in problem number 6, we wanted to find z sub alpha over 2, which was 0.01 over 2, which is z sub 0.05. So to find that, if you're putting 0.005 of the area in the right tail, that means the rest of it, 0.9950, is in the left tail. And what you would do is you would look for a value as close as possible to that in your z table. And I think I mentioned, but I didn't actually show, that there's a special one for 0.9950, simply because that one's used quite so often. And it's right down here. 2.575 is what you get, or where you find 0.9950 of the area. So that one, and another one that you run into quite often is 1.645, and that puts 5% of the area in the right tail and 95% in the left tail. Okay? Yeah, thanks for the question. Okay. Let's try another one. Let's take a look at problem number 24. In a Harris poll of 514 human resource professionals, 90% said that the appearance of a job applicant is most important for a good first impression. So, among the 514 surveyed, how many of them actually said that the appearance of a job applicant was important for a good first impression? How am I going to find that number? Yeah, 514 times 90%. It's just, they didn't exactly give you X. They gave you P hat. So we have to go calculate X. So problem 24, N equals 514. X is going to be 514 times 90%. $462.6. Something looks a little wrong there. Yeah, the 0.6, right? We don't chop a human resource person in half, at least usually. So, what should I round this to? Yeah, I'd do 463. That's the closer of the two integers that surround this number. So our number of successes then, we'll count it as 463. All right, so that's the number that actually succeeded here. Now it tells us to construct a 99% confidence interval for the estimate of the proportion of all human resource professionals. So our P hat is going to be 463 divided by 514. It's about 90% without calculating the exact decimal. But the good news is that we don't have to. Let's move over to StatDisk and let it do some of our heavy lifting. The sample size is 514, and we had 463 successes. We've got our confidence level in, so bang, evaluate. So, okay. This is a nice tight confidence interval. And you want this one right here, not the Wilson score. We're going to be sticking with this one using the normal approximation. So let's see, we've got 0.866812 less than P less than 0.9347. All right, we don't need a ridiculous amount of digits. A little OCD compelled me to write all these down. Let's round this off to about 0.8668 and then 0.9347. So that's our confidence interval. Should make this look more like a P and less like a rho. We can be 99% confident. And here what you're restating is what this is. 99% confident that the true proportion of human resource professionals, let me just get a little bit lazy, HRP, who said that the appearance is the most important factor. Appearance is the most important factor is between, and then we'll just list our percentages here. 86.68 less than percentage and 93.47%. So it's somewhere in there. We don't know where it is because we didn't poll every single human resource professional, but our sample suggests that it was about 90%, allowing for some variability, okay, between about 86.68 and 93.47. Let's figure out what E is for this. Now, we're not going to do it based on the formula. Rather, we're just going to do it based on the knowledge that what this is really is P hat minus E and P hat plus E. So if that's P hat minus E or P hat plus E, what would you estimate the error term to be? Well, if this is about 90%, and without actually calculating it, if this is about 90%, then the error rate is about 0.0347, maybe a little bit less. Let's find out. 0.9347 minus P hat, which was 463 divided by 514. So about 3.4%. That's not too bad. When you look at national polls, a lot of times national polls will have an error of about 3%. And that's where that error is coming from. All right. Questions on this one? One thing that I'm going to put the emphasis on is being able to relate your conclusion, to kind of take it away from their stat class and put it in terms that people can understand. Somebody who's not taking a stat class. That's going to be an important thing moving on from here, because not everyone takes stats. Yes? You can use either one, whatever you're most comfortable with. Yeah. I'm more than happy to have people use StatDisk. That's fine. Now, one thing that sometimes you want to do, sometimes you might look at that and go, you know what? I need to be more precise about where that's at. I need to know to within 1%, or whatever value you want. So you want to control the size of your error. Well, the only thing that we can do to control the size of that error for a particular level of confidence is you can control your sample size. If you control your sample size, we can make this thing as small as you want. So if you take this formula and solve it for n, then you get an expression that allows you to come up with a sample size to meet your requirements. So that expression is this: n equals z sub alpha over 2 squared times p hat times q hat divided by the square of the error. Now, this is assuming you have an estimate for p hat and q hat. If these are unknown, replace p hat times q hat by 0.25. So if you don't know what those are, that's fine. We'll take that out of the equation and just write in a 0.25. So this is a way you can kind of figure out, well, how big of a sample do I need if I want to limit my error? So a quick example like that would be problem number 30. Find the sample size needed to estimate the percentage of robberies in Texas that resulted in arrest. Use a 0.04 margin of error. So what that is that's your E. And a confidence level of 80%. So 80% equals 1 minus alpha. That means alpha is going to be 20%. That's a really, really big alpha. Alpha is typically 10% or even better yet 5% or less. So it's a really, really big alpha. So alpha in problem number 30 is 0.20. If I need z sub alpha over 2, that's going to be z sub 0.20 over 2 or z sub 0.10. Let's just get that off of Google Sheets here. So norm inverse. If I want z sub 0.10, that's 10% of the area in the right tail or 90% of the area in the left tail. So about 1.28. And that's the value you should get from your z distribution if you look it up that way. E was given to us as 0.04, but we don't know p hat or q hat. So instead of p hat times q hat, I'll use 0.25. So here's my calculation. You're going to square your z sub alpha. I'm putting this in place of p hat, q hat because we don't have the numbers themselves. And divide by the square of the area. Square of the error. .28, hit the squared key, times 0.25, divided by 0.04, and again hit the squared key, which is on the left-hand side of your calculator. 256. So that would be your sample size that you need to control your error here. Any questions on problem number 30 here? For homework, try problems 1 through 35.